Move the entire universe 10 meters to the left. Every star, every atom, every person, with all the distances between them, left exactly as they are, the whole thing shifted. Has anything changed? Isaac Newton said yes, and built his physics on it. A philosopher named Leibniz said the question is broken because there is nothing there to shift. 310 years later, nobody has settled it by argument. But here is what that story leaves out. Physics found a third answer, in a place almost nobody looks. Underneath both space and time, there is a single structure, a bare list of which events can influence which, and nothing else. And a series of theorems, from 1914 to 1977, showed that this one list determines 9 of the 10 numbers you need to describe the shape of reality at every point in the universe. The 10th is just counting. So what are space and time actually made of? By the end of tonight, you will know exactly. Settle in, hit subscribe if you're new here, because by the end of this, the word where will never mean quite the same thing again. Now, let's slowly ease into this. Part 1. The 2 things you never look at. There are 2 things you have used every second of your life and have almost certainly never examined. You have examined a great many other things. You have wondered whether atoms are mostly empty. You have wondered whether the universe goes on forever, whether anything else out there is alive, whether the world you see is the world that is actually there. Those are good questions, and people have spent lifetimes on them. But every single one of them was asked somewhere, and every single one of them was asked some moment. The somewhere and the moment came along for free. They were not part of the question. They were the conditions under which a question was possible at all. Space and time are the last things anyone thinks to interrogate, and the reason is structural rather than lazy. You cannot step outside them to get a look. Every measurement ever made was made at a place and at a time. Every experiment, every observation, every thought you have ever had about anything at all happened inside the 2 things we are about to take apart. When physicists say that space and time are the hardest problems in the subject, this is a large part of what they mean. It is not that the mathematics is difficult, although it is. It is that the investigator is standing on the thing being investigated. So let us start with something small and concrete. Hold out your hand and leave a gap of about 10 centimeters between your finger and your thumb. Now answer a simple question about that gap. What is in it? The easy answer is nothing, or air, and the easy answer is beside the point. Take the air out. Take out the dust, the water vapor, the photons drifting through, the neutrinos passing without noticing. Take out the fields, if you can imagine that. What is left between your finger and your thumb? You will find that you have 2 instincts about this, and that they contradict each other. The first instinct says that something is left. There is a gap. The gap has a size. 10 centimeters of genuine physical space is sitting there between your fingers, a piece of the same continuous stuff that stretches out through the room, past the walls, past the atmosphere, past the moon, and on across the galaxy. On this view, space is a thing. It is the container the universe is kept in, and it would be there whether or not anything was in it. The second instinct says the opposite. There is no stuff between your fingers. There is only the fact that your finger and your thumb are apart, and that fact is a relationship between 2 objects, not a substance sitting in a gap. On this view, space is not a thing at all. It is a way of talking about how objects stand to one another. Remove every object in the universe, and you do not get an empty stage. You get nothing, because there was never a stage. There were only the actors and the distances between them, and distances are not made of anything. Both of those instincts feel obvious. Only one of them can be right, and physics has been arguing about which one for 339 years without producing an answer that everybody accepts. Now do the same thing with time, which is harder, because time does not sit still while you inspect it. Something happened a moment ago. Something is happening now. Something will happen next. The usual picture is a river, a current that carries everything along at a fixed rate, 1 second per second, whether or not anything is in it. Empty the universe, and time would still be passing, silently, with nothing to mark it. The other picture says that this is backwards. There is no river, there are only events, and events happen in an order, and time is the name we give to that order. Nothing flows. Things happen, one after another, and the after is the only thing that is real. Here is why this matters more than it sounds like it should. These are not two ways of speaking about the same underlying facts. They are two different claims about what exists, and underneath both of them, underneath the argument about space and the argument about time, there is a single concept that decides the outcome for both at once. That concept is not obscure. It is not new. It appears in every general relativity textbook printed in the last 50 years. It is the thing that professional relativists reach for first when they want to know what a space-time is really like, and it is almost never mentioned in any popular account of physics. Most people who can define a light year, who can explain time dilation at a dinner party, who know that gravity bends light and that the universe is expanding, have never met it. You can go a very long way without it. You can use space and time fluently, for a lifetime, the way you can drive a car without knowing what a differential does. It works. Right up until the moment you want to know what is actually happening, why a black hole has an edge, why the beginning of the universe is a beginning, why the most direct attempt to write down the quantum state of everything produced an equation in which nothing ever happens. And then you find that every one of those answers is written in a language you were never taught. By the end of tonight, you will know what that concept is. You will know who first noticed it, in 1914, working alone and largely ignored. You will know the 3-page proof from 1964 that showed the entire structure of Einstein's relativity falls out of it and nothing else. You will know the theorems from the 1970s that established, in curved spacetime, in the real universe with gravity in it, that this one concept determines 9/10 of everything there is to know about the shape of reality. And you will know exactly what the missing tenth is and where it comes from. And you will know why a small number of very serious physicists now think that space is not fundamental at all, that it is a summary, a large-scale description of something underneath, in roughly the way that temperature is a summary of jostling molecules and not a substance in its own right. Before any of that, though, we have to go back to a bucket of water on the end of a twisted rope, and to a question that a German philosopher asked an English mathematician about moving the entire universe 10 meters to the left. Part 2. The Bucket and the 10 meters. In July of 1687, Isaac Newton published the book that made physics a quantitative science, and before he wrote down a single law of motion, he wrote down something else. In the opening scholium of the Principia, before the laws, before the proofs, before the machinery that would predict the tides and the orbits and the return of a comet, Newton stated what he thought space and time were. Absolute space, he wrote, in its own nature, without relation to anything external, remains always similar and immovable. Absolute, true and mathematical time, of itself and from its own nature, flows equably without relation to anything external. Read that again slowly, because it is doing something unusual for Newton. It is not a result. Nothing in the Principia proves it. It is a declaration about the furniture of reality, placed at the front of the most successful physics book ever written, and stated with the confidence of a man who considers the matter settled. Space is a container. It is always there, it never moves, and it does not care what is in it. Time is a current, running at a fixed rate everywhere, and it would run at that rate in a universe containing nothing whatsoever. Newton needed this. His laws only work in certain reference frames, the ones we call inertial, where a body left alone travels in a straight line at constant speed. If you try to define an inertial frame without absolute space, you find yourself going in a circle. An inertial frame is one in which the laws hold, and the laws hold in inertial frames. Absolute space cut the circle. It gave him a fixed backdrop against which motion could be real motion, rather than a matter of opinion. He also had an argument, and it is a good one. It involves a bucket. Take a bucket of water and hang it from a cord. Twist the cord tightly and release it. At the first instant, the bucket begins to spin, and the water inside does not. The bucket is rotating rapidly, relative to the water, and the surface of the water is flat. Wait. Friction gradually drags the water into rotation with the bucket, until the two are turning together, at rest relative to each other. And now the surface of the water is not flat. It has climbed the walls into a curve, hollowed out in the middle. Now grab the bucket and stop it. The water keeps spinning. The bucket and the water are once again in rapid relative motion, and the surface stays curved. Look at what that sequence establishes. When the bucket and water were in relative motion, the surface was flat. When they were at relative rest, the surface was curved. The shape of the water does not track the relative motion at all, so the curvature cannot be caused by rotation with respect to the bucket. It cannot be caused by rotation with respect to the room, either, or the earth, or anything else you might reasonably point at, because the water's behavior is exactly the same wherever you take the experiment. Newton's conclusion was direct. The water knows it is rotating, and what it is rotating with respect to is absolute space itself. That argument stood for 200 years, and honestly, it is still the strongest weapon the container view ever had. Rotation leaves marks. Spin a bucket, or a planet, or a galaxy, and something physical happens. The surface curves, the equator bulges, the arms wind out. Uniform motion in a straight line you cannot detect at all, but acceleration and rotation seem to be detectable from the inside, with the curtains closed, without reference to anything outside. That looks very much like a system noticing its motion relative to space itself. Then came the objection, from a man who never held a chair in physics and never ran an experiment in his life. Gottfried Wilhelm Leibniz was a lawyer, a diplomat, a mining engineer, a designer of calculating machines, and the co-inventor of the calculus, which is what he and Newton were mainly busy hating each other about. But his objection to absolute space had nothing to do with priority disputes. It came out of a principle he applied to everything. Nothing is the case without a sufficient reason for it being that way, rather than some other way. Leibniz said that space is not a thing. Space, in his phrase, is an order of coexistences, a way of describing how things stand in relation to one another, in the same way that a family tree is a way of describing how people stand in relation to one another, and not an object hanging in the air behind them. Time, likewise, is an order of successions, not a river, a sequence. And then he asked the question that has been sharpening minds ever since. Suppose you took the entire universe, every particle, every planet, every observer, every field, with all the distances between them left exactly as they are, and moved the whole thing 10 meters to the left. Would anything be different? Newton is committed to saying yes. The matter now sits at different absolute positions. It is a genuinely different state of the world, even though nobody could ever detect the change, because detecting it would require a fixed marker outside the universe to measure against, and there isn't one. Leibniz says the question is broken. Nothing measurable differs. Not one relationship has changed. Every distance, every angle, every possible observation is identical. There is no fact of the matter about where the universe sits, because where the universe sits is not a meaningful description of anything. And if God, Leibniz is writing in 1716, so God is doing the work that the laws of nature would do in a modern paper. If God had to choose between placing the universe here and placing it 10 meters to the left, there would be no reason to prefer either. Therefore there is no choice to make. Therefore there are not two options. There is one universe, described twice. This exchange happened in writing, and it happened fast. Between November of 1715 and November of 1716, Leibniz and Samuel Clerk, an English clergyman and philosopher, Newton's ally, and to a significant degree Newton's mouthpiece, traded 5 letters and 5 replies. The go-between was Caroline, Princess of Wales, who had studied under Leibniz, corresponded with him for years, and appears to have set the whole thing up deliberately because she wanted the argument on the record. It is one of the most consequential debates in the history of science, and it did not end. It stopped. Leibniz died in November of 1716, with his 5th paper unanswered, and Clerk published the correspondence the following year, in a handsome bilingual edition, with himself having the last word in print. That is roughly how the argument was received for the next century and a half. Newton won, mostly because Newton's physics worked and could put a planet where you predicted it would be, and because the other man was no longer in a position to reply. But nothing had been settled. Leibniz's question had not been answered. It had been outvoted. And there was one thing his account could not handle at all, one thing that Newton's bucket kept quietly sitting there doing, spinning on its cord with its water climbing the walls, waiting for someone to explain it. If space is nothing but the relations between objects, then what, exactly, is that water rotating with respect to? It would take 167 years for anyone to produce a serious answer, and when it came from a physicist who thought the entire question of what things are was a distraction from what can be measured. Part 3. The Argument Nobody Could Settle. Ernst Mach published The Science of Mechanics in 1883, and it is not really a physics textbook. It is a historical and critical examination of how physics got its ideas, written by a man with an unusually severe standard for what counts as a real statement about the world. Mach's rule was simple and merciless. If a claim cannot in principle be checked against a sensation, a reading, an observation, then it is not physics. It is decoration. Absolute space failed that test immediately. Nobody had ever seen it, measured it, or detected a single one of its properties. It appeared in Newton's system as a piece of scaffolding that did essential work while remaining permanently invisible. Mach found this intolerable, and he went straight for the bucket. His counter-argument is one sentence, and it has been quoted for 140 years because it does so much damage with so little effort. Newton, he pointed out, had performed an experiment with a thin metal pail containing a few liters of water and had drawn a conclusion about the structure of the universe. But nobody, Mach wrote, is competent to say what would happen if the sides of the vessel were increased in thickness until they were several leagues thick. Think about what that does to the argument. Newton's inference depends on the claim that the surrounding matter is irrelevant, that the water's behavior has nothing to do with the bucket, because the bucket is small. Mach's reply is that the bucket is small, so of course its effect is undetectable, and that proves nothing at all about whether matter is what the water is responding to. Make the bucket the size of a mountain range. Make it the mass of a planet. Nobody has run that experiment, and until someone does, the conclusion is unsupported. What, then, is the water rotating relative to? Mach's answer was, relative to everything else. Relative to the total distribution of matter in the universe, the fixed stars, in the language of the day, which meant the entire visible cosmos. Inertia is not a property a body has by itself, sitting alone. It is a relationship between that body and all the other matter there is. Take away the stars, and rotation stops meaning anything. because there is nothing left for the rotation to be relative to, and a lone bucket in an otherwise empty universe would have no way to curve its water. This is relationalism with something at stake. It is not a philosopher's word game about 10 meters to the left. It is a physical claim. Local inertia is determined by distant matter. It says the reason it is hard to push a heavy object here has something to do with the mass of galaxies you will never visit. Newton had anticipated something like this reply, and had a harder version of the bucket waiting for it. Instead of water in a pail, imagine two spheres connected by a cord, floating in a universe that contains nothing else at all. If the pair is rotating, the cord will be under tension, and you could measure that tension from inside the system without ever looking outside it. Rotating with respect to what? Mark's answer requires distant matter, and in this version, there is none by construction. The relationalist has to say either that the tension would not appear, which nobody can test, or that the thought experiment is illegitimate because a universe containing only two spheres is not a universe that could exist. Both replies are uncomfortable, and both are still being made. A young patent clerk in Bern read Mach and was changed by it. Einstein said repeatedly that Mach's critique had been decisive for him, that it was the book that taught him to distrust concepts which could not be cashed out in observations. When he built general relativity, he expected the finished theory to deliver Mach's idea in mathematical form. In 1918, he gave it a name, calling it Mach's principle, and for a while he believed his field equations had embodied it. Here is where the story turns awkward, and the awkwardness is the honest part. General relativity is Machian in some respects. It says, unambiguously, that matter determines the geometry of space-time, and that the local standards of what counts as unaccelerated motion are set by that geometry. Spin a massive body, and it drags the local definition of not rotating around with it. This is called frame dragging, and for decades it was a prediction on paper. Then a satellite went up to check. Gravity Probe B launched in April of 2004, carrying 4 gyroscopes that are among the most perfectly spherical objects human beings have ever manufactured. Fused quartz spheres, round to within about 40 atomic layers. If you scaled one to the size of the Earth, its tallest mountain would be a couple of meters high. The satellite pointed at a guide star and watched, for a year, to see whether the spin axes of those gyroscopes drifted. They drifted. The larger effect, geodetic precession, comes from the curvature of space-time around Earth's mass, and it came in at roughly 6,600 milliarc-seconds per year, matching prediction to about 0.3%. The smaller effect, frame dragging, comes from Earth's rotation twisting space-time around with it, and it came in at about 37 milliarc-seconds per year, an angle so small that if you drew it on the sky, it would take something like 100,000 years to sweep across the width of the full moon. It matched prediction to about 19%. A second, completely independent measurement came from a much cruder method. The Lagios satellites, and later Lares, are passive metal spheres, studded with mirrors, put into orbit, for no purpose other than to have lasers bounced off them from the ground. By tracking the positions of those spheres for years and watching the orientation of their orbits creep around the Earth, teams were able to extract the same frame-dragging effect at the level of a few percent, using nothing but reflected light and patience. 2 very different techniques, one exquisite and one blunt, found the same twist in space-time. That is Mach's intuition, partly vindicated by a machine in orbit. Rotating matter really does drag the standard of rotation around with it. The stars really are involved in what it means to spin, but only partly, because general relativity also permits solutions with no matter in them whatsoever that still possess a perfectly well-defined inertial structure, empty universes in which not rotating has a meaning, which is precisely what Mach said should be impossible. It permits universes that rotate as a whole, with nothing outside for them to rotate relative to. Einstein noticed this, and it bothered him for the rest of his career. He gradually stopped claiming that his theory implemented Mach's principle, and by the end, he had largely stopped talking about the principle at all. So the argument between the container and the relations did not get resolved. It got inherited. General relativity took Newton's fixed stage and made it flexible. It can stretch, bend, ripple, and carry energy, and in doing so, it made the stage far more thing-like than Newton had ever claimed, because Newton's absolute space could not do anything, and Einstein's can. It also made the geometry depend on the matter, which is what a relationalist wanted. The theory says yes to both sides in different sentences, and that is where the question would have stalled permanently, if the same theory had not quietly handed over a completely different way of asking it. Because tucked inside relativity, underneath the curvature and the field equations and the ripples in space-time, there is a structure that is neither a container nor a set of distances between objects. It is a pattern of which events can reach which. And in 1905, when Einstein first wrote it down, nobody, including Einstein, noticed that it was the important part. Part 4. The Weld. Einstein's paper of June 1905 did not set out to say anything about the nature of space. It set out to fix an embarrassment. The embarrassment was this: take a magnet and a loop of wire. Move the magnet toward the loop, and a current flows. Hold the magnet still, and move the loop toward the magnet, and the same current flows, of exactly the same size. But the textbook explanations of those two situations were completely different. In the first case, a changing magnetic field creates an electric field, which pushes the charges. In the second case, there is no changing field at all. Instead, the charges are moving through a static field and feel a magnetic force. Two different mechanisms, two different sets of equations, one identical result, every time, without exception. Einstein's first paragraph says, in effect, this cannot be a coincidence, and if the outcome depends only on the relative motion, then the theory should say so from the start. He took the sameness as the deeper fact and rebuilt mechanics around it. The consequences arrived quickly, and they were not gentle. If the speed of light is the same for every observer, regardless of how that observer is moving, which is what the electromagnetic theory demanded, and what every experiment kept confirming, then moving clocks run slow, moving objects are shortened along the direction of motion, and, most dangerously, two events that one observer judges to happen at the same moment are judged by another observer, moving relative to the first, to happen at different moments. That last one is the load-bearing wall coming down. The relativity of simultaneity does not say that we have trouble synchronizing our watches. It says there is no fact of the matter about which distant events are happening now. Two observers passing each other, both perfectly competent, both using flawless instruments, will produce different lists of what is currently going on across the universe, and physics offers no way at all to say which list is correct, because there is nothing for correctness to mean. Newton's universal river of time, flowing equably everywhere without relation to anything external, was gone, not slowed, not adjusted. There is no such thing as a moment in the universe. There is only a moment for someone. It is worth pausing on how large that disagreement can get, because the usual examples involve spaceships at implausible speeds and give the impression that the effect is a curiosity. It is not. The size of the disagreement about simultaneity grows with distance. For two events separated by a single light-year of space, an observer moving at 30 kilometers per second relative to another, which is not a spaceship speed, it is simply the speed at which the Earth goes around the Sun, will place those events about 100 seconds apart in time from each other's judgment. Push the distance out to millions of light years, and ordinary walking speed is enough to shift the disagreement into days. We will come back to that later, in a way you may not enjoy. The person who saw what had actually happened was not Einstein. It was his old mathematics teacher. Hermann Minkowski had taught Einstein in Zurich and had not been impressed, later describing him privately as a lazy dog who never bothered about mathematics at all. But when Minkowski read the 1905 paper, he recognized something Einstein had not made explicit. The strange effects were not a collection of separate distortions. They were the shadows of a single geometric structure, and if you wrote them down in 4 dimensions instead of 3, they became almost simple. On the 21st of September, 1908, at a meeting of German natural scientists and physicians in Cologne, Minkowski stood up and opened his lecture with a line that has outlived almost everything else said at that conference. The views of space and time which he wished to lay before them, he said, had sprung from the soil of experimental physics, and therein lay their strength. They were radical. Henceforth space by itself, and time by itself, were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. The union is not poetry. It is a specific quantity, and it is the reason the lecture mattered. Take 2 events, any 2 things that happen. Measure how far apart they are in space, and how far apart they are in time. 2 observers moving relative to each other will disagree about both numbers, and neither is wrong. But take the distance between them in space, square it, and subtract the time between them, multiplied by the speed of light, also squared. That combination, that particular subtraction, comes out identical for every observer in the universe, no matter how they are moving. It is called the space-time interval, and it is the thing that is actually there. Everything you have ever heard about relativity being about how everything is relative gets this exactly backwards. Relativity is a theory about what is absolute. Individual measurements of space and time turn out to be perspectives on something else, the way the length of a shadow is a perspective on a solid object. Change your motion, and the shadow changes shape. The object does not. And the entire content of the theory is hiding in one character, the minus sign. If that combination were a plus, distance squared plus time squared, then time would simply be a 4th direction, and space-time would be ordinary 4-dimensional space, with a strange unit on one axis. There would be no light barrier, no causal structure, no distinction between past and future. It is the minus sign that makes time different in kind rather than in name, and it is the minus sign that sorts the universe into categories. There is a piece of mathematical sleight of hand from this period that is worth knowing about, because it has quietly misled generations of students. Henri Poincaré, working on the same problems slightly earlier, noticed that if you write the time coordinate as an imaginary number, the minus sign disappears into the algebra, and the interval looks like an ordinary sum of 4 squares. It works. The calculations come out right, and it leaves people with the impression that space-time is just 4-dimensional space wearing a disguise, which is exactly wrong. The minus sign is not a bookkeeping convention that can be absorbed. It is the physical difference between a direction you can turn around in and a direction you cannot. Because that combination, the interval, can come out 3 ways. It can come out negative, which happens when 2 events are separated by more time than the distance light could cover between them. Such a pair is called time-like separated, and something traveling slower than light can be present at both. You, sitting where you are now, and you, sitting there in 1 minute, are time-like separated. It can come out exactly 0, which happens when the separation is precisely what light would cover. A flash leaving a star and that same flash arriving in your eye are separated by an interval of exactly nothing, no matter how many light years lie between them. This is called null separation. Or it can come out positive, which happens when two events are farther apart in space than light can bridge in the time available. That pair is called space-like separated, and no object, no signal, no influence of any kind can be present at both. Nothing traveling at any speed permitted by physics connects them, ever. That threefold sorting looks like a technicality. It is the concept this entire video is about, and we have just met it without naming it. Minkowski did not get long to develop the idea. Less than 4 months after the Cologne lecture, in January of 1909, he died of a ruptured appendix. He was 44. Einstein's initial reaction to the geometric reformulation had been dismissive. He called it superfluous learnedness, and grumbled that since the mathematicians had taken over relativity, he no longer understood it himself. Within a few years, he had changed his mind completely, and for a concrete reason. When he tried to extend relativity to include gravity, he found he could not take a single step without Minkowski's four-dimensional geometry. General relativity is written in the language of a man who did not live to see it used. But there is something buried in the three-way sorting that Minkowski's audience in Cologne did not stop to examine, and that most people who learn relativity today still do not have pointed out to them. The categories are not really about distance, they are about something else entirely, and once you see what they are actually sorting, the light barrier stops being a speed limit and becomes something far stranger. Part 5. What relativity actually forbids. Pick an event. Anything will do. A match struck in a dark room. An atom in a smoke detector giving up a particle. A word spoken out loud at a particular instant, in a particular kitchen. Light leaves that event in every direction at once, spreading outward as a sphere that grows at 300,000 kilometers per second. After 1 second, the sphere is 300,000 kilometers across in radius, which is most of the way to the moon. After 8 1/3 minutes, it has swallowed the sun. After 4 and a bit years, it has reached the nearest star. It never stops growing, and it never slows down. Now draw that on paper, with space running across the page and time running up it. The expanding sphere becomes a cone, opening upward into the future. And because the same logic runs backwards, light was arriving at that event from all directions before it happened, there is a matching cone opening downward into the past. 2 cones, meeting at the event, one above and one below. This is the light cone, and it is usually introduced as a picture of where light goes. That is the smaller half of what it is. The cone is the boundary of influence. Any event lying inside the future cone can be reached by something moving slower than light, a particle, a signal, a hand, a chain of 10,000 intermediate causes, which means the first event can be a cause of it. Any event lying outside the cone cannot be reached by anything. Not by a slow process, not by a fast one. There is no sequence of physical events, however clever, however indirect, that starts at the first and arrives at the second. They are causally sealed off from each other, permanently, and no technology and no future discovery changes that, because it is not a limitation of technology. That is what relativity forbids. Not motion faster than light. That is the classroom version. What it forbids is influence outside the cone. The cone is a statement about causation, and the speed of light is simply the number that sets its slope. Now here is the part that makes the whole structure fit together, and it is the most quietly astonishing thing in special relativity. Take 2 events inside each other's cones, time-like separated, capable of influencing one another. Every observer in the universe, however they are moving, agrees which one came first. The order is absolute. There is no reference frame, no speed, no clever trick that reverses it. If the match was struck before the room lit up, then in every possible description by every possible observer, the match was struck before the room lit up. Now take 2 events outside each other's cones, space-like separated, incapable of any influence in either direction. Observers flatly disagree about the order, and no answer is privileged. One observer says A happened first, another says B happened first, a third says they were simultaneous. All three are correct, and the question of which really came first has no content. Put those two facts side by side and look at the seam between them. Relativity scrambles the order of events exactly, and only in the cases where no causal relationship is possible. It preserves the order absolutely, in exactly, and only the cases where one event might have caused the other. The disagreement is confined, with perfect precision, to the pairs where it cannot matter. That is not a coincidence, and it is not a patch. It is what the theory is made of. Relativity will never let two observers disagree about whether a cause preceded its effect. It only lets them disagree about pairs of events where causation was never on the table in the first place. The relativity of simultaneity, which sounds like the theory throwing away objective truth, turns out to be the theory protecting objective causation and throwing away only the parts that had no causal content. It also explains something that is usually taught as two separate rules. Traveling faster than light and traveling backwards in time are not two different impossibilities that happen to sit next to each other in the textbook. They are the same impossibility described from two different frames. A signal that outruns light in one observer's description arrives before it left in another observer's description, and both descriptions are equally valid. So the moment you allow anything outside the cone, you have allowed effects to precede their causes, and the absolute ordering that protects causation collapses. The cone is not a wall built to keep travelers in. It is the shape of the guarantee that things happen in an order. Space-like separation is not an exotic or astronomical condition either. Two events, 1 meter apart, and less than about 3 billionths of a second apart in time, are already outside each other's cones. This is why the timing electronics in certain quantum experiments are engineered so obsessively. To prove that two measurements could not have communicated, the experimenters have to make the pair of measurement events space-like separated, which at laboratory distances means winning a race against light by nanoseconds. Once you have seen that, the speed of light stops looking like a fact about light. Light travels at that speed because light is massless, and anything massless is obliged to travel at exactly that speed. But the speed itself is prior. It is the conversion factor between space and time, the number that decides which pairs of events are causally connectable at all, the slope of the cone. Turn every light source in the universe off, and the structure would be exactly where it was. A better name for it, which some physicists now use deliberately, is the speed of causality. You can check that this is a structural limit rather than a fact about photons, because other things use the same cone. On the 17th of August, 2017, the gravitational wave detectors in Louisiana and Washington and the detector in Italy registered the final spiral of two neutron stars merging. Gravitational waves are not light. They are not made of photons. They are not electromagnetic. They are not produced by the same mechanism or detected by the same physics. They are ripples in the geometry of space-time itself, and they were detected by measuring the length of a 4-kilometer arm, changing by a fraction of the width of a proton. 1 3/4 seconds after that signal, a gamma-ray burst arrived from the same patch of sky. The event had taken place roughly 130 million light-years away. Sit with those two numbers. 130 million years of travel. 1 3/4 seconds of difference on arrival. And that small gap is best explained by the gamma rays taking a moment to escape the wreckage, not by any difference in speed. The measurement pins the difference between the speed of gravity and the speed of light to within a few parts in 1,000 million. Gravity and light share no mechanism whatsoever. What they share is the cone. Two entirely different phenomena obey the same limit, because the limit was never about either of them. There is one more thing to say about cones before we go looking for who first realized what they were, and it is the personal version. You have a past light cone. Everything you have ever seen, everything you have ever heard, every particle that has ever touched you, every event that has ever affected you, in any way whatsoever, lies on or inside it. It is not a region of space. It is a region of history, and it tapers down to a single point at the moment you began. Everything outside it has never been able to reach you, and never will have been able to. And you have a future light cone, the complete set of events you could still, in principle, affect. It opens ahead of you, and it widens forever, and everything outside it is beyond your reach, in the most absolute sense the universe has, not far away, but disconnected. Every human being is a small pair of cones, moving through a structure of relations that decides in advance what can ever matter to them. For 50 years after Minkowski drew those cones, everyone treated them as a consequence, a picture you could derive once you already had the geometry of space-time, the distances, the durations, the metric. One man, working almost entirely alone in Cambridge, went the other way round. Part 6. The geometry hiding inside the word after. Alfred Arthur Robb was born in Belfast, studied at Cambridge, spent a period in Göttingen, and then went back to Cambridge and worked mostly on his own for the rest of his career. He is not a famous man. He does not appear in the popular histories. He never held a major chair. He founded no school, and he had almost no students. What he had was a question that nobody else had thought to ask. Everyone in 1912 was busy working out the consequences of relativity. Robb wanted to know what relativity was made of, and in 1914 he published a book with Cambridge University Press called A Theory of Time and Space, in which he tried something that reads, even now, as slightly reckless. He threw away distance, he threw away duration, he threw away clocks, rulers, coordinates, simultaneity, velocity, and the metric. He kept exactly one thing, a relation between events, which he expressed as after. That is the entire vocabulary. Given two events, either the second is after the first, or it is not. After means, in physical terms, capable of being influenced by, inside the future cone. There are no numbers anywhere. There is no notion of how much later, or how far away, or in which direction. There is only a bare pattern of which events lie, in which other events' futures, the same list you would get by going through every pair of events in the universe and making a single mark, yes or no. From that, and a short list of postulates about how the relation behaves, Robb reconstructed the whole of Minkowski's geometry. The light cones, the dimensionality of space-time, the distinction between time-like and space-like, the Lorentz transformations, the interval, all of it derived from a structure that contains no measurements at all. The book is written in an axiomatic style so austere that it was admired more than it was read. Robb worked in near isolation, drew his own diagrams of what he called the conical order, light cones, decades before they became standard classroom furniture, and stated in his preface the thing he thought he had shown, that the relation of before and after is the fundamental one, and that in some sense, time is more basic than space. Then the field moved on without him. For roughly half a century, his results sat in the literature being cited by almost nobody. He had been building toward it for years. An earlier book, Optical Geometry of Motion, had appeared in 1911, and it already contained the instinct that would define his work, that the physics of light is not really about light, but about the order in which things can be seen to happen. The 1914 book took that instinct as far as it could go, and then rather further than the readership of the time was willing to follow. Let me try to make what he did visible, because in the abstract it is easy to nod along without registering the size of it. Imagine you are handed a ledger. It is unimaginably large, one line for every pair of events that has ever happened anywhere in the universe. and every line contains exactly one mark. Yes, if the first event could have reached the second. No, if it could not. That is all the ledger says. There are no distances in it. No dates, no durations, no coordinates, no clock readings, nothing you could call a measurement. You open it somewhere in the middle and start working. You notice that certain events form long chains, each one reachable from the last, and you realize you are looking at the history of an object, a stone, a star, a person. You notice that some chains are dense with connections to their neighbors, and others are sparse, and the pattern of connection begins to look like proximity. You notice regions where the yeses and nos twist, where the pattern of what can reach what leans systematically to one side, and you find you are reading curvature, a mass, a gravitational field, an orbit. You keep going. You find a region from which almost nothing gets out, where the chains all lead inward and none of them lead back, and you have found a black hole without anyone telling you black holes exist. You can build the entire universe out of this ledger, the shape of every galaxy, every orbit, every wave, every horizon, every collapse, and then you sit back and realize what you cannot do. You cannot say how big anything is. Not the black hole, not the galaxy, not the room. The ledger will give you the shape of everything and the size of nothing. Hold on to that. It becomes the whole story later. 50 years after Rob's book, in 1964, a British mathematician named Christopher Zeeman published a paper in the Journal of Mathematical Physics that ran to about 3 pages. It is called Causality Implies the Lorentz Group, and the title is also the summary. Zeeman asked a question that sounds technical and is not. Suppose you have the causal ordering of spacetime, just the yeses and nos, just the pattern of what can influence what. Now ask which transformations leave that pattern exactly as it is. What can you do to spacetime without changing a single entry in the ledger? The answer he proved is that there is almost nothing you can do. You can rotate, you can translate, shift everything over. You can perform a Lorentz transformation, which is what happens when you change to a frame moving at a different speed. And you can rescale the whole thing, making everything uniformly bigger or smaller. That is the complete list. Nothing else preserves the causal order. Look at what that means. The symmetry group of special relativity, the entire machinery of boosts and rotations that generates time dilation, length contraction, the relativity of simultaneity, the invariant speed limit, every counterintuitive result the theory is famous for, is precisely the group of transformations that leaves the causal order alone. It is not an additional structure that had to be discovered separately and layered on top. It is what causality looks like when you write it in coordinates. It is worth saying that the proof itself is not difficult. It is short, and a determined undergraduate can follow it. What was difficult was believing the question was worth asking, that anyone would bother to strip relativity down to a bare ordering and check what was left. Zeeman spent most of his career in topology and is better known outside relativity altogether. This was a short excursion into someone else's subject that quietly relocated its foundations. Notice also the one piece of freedom on that list, because it is the loose thread of this entire video. You can rescale. You can make the whole structure uniformly larger or smaller, and the causal order does not notice. Whatever the causal ordering knows about the universe, it does not know how big it is. Zeeman was scrupulous about credit, and noted in the paper that the essential result had already been obtained more than a decade earlier by the Russian geometer Alexandrov, whose work had gone largely unnoticed in the West. Alexandrov had also shown something else along the way, that you can build the entire topology of spacetime, the notion of which regions are near which, what counts as a neighborhood, what continuity means, out of causal diamonds alone. Take all the events after A and before B, use those double cone regions as your basic building blocks, and the topology of the universe assembles itself out of nothing but ordering. So by the middle of the 1960s, two results were sitting in the literature, both largely ignored, both saying the same thing from different directions. Rob, you can build Minkowski geometry out of after. Zeeman and Alexandrov, the symmetries and the topology of relativity are exactly the symmetries and topology of the causal order, and nothing more. Both of those results, though, applied to flat spacetime, the idealized case with no gravity in it. The real universe is curved. Matter bends it, and the bending is the whole subject of general relativity. The obvious question is whether any of this survives when you turn gravity on. It took another decade to find out, and the answer, when it came, was more extreme than anyone had reason to expect. Part 7. 9 parts out of 10. To describe the geometry of a curved spacetime completely, you need 10 numbers at every point. That is not an arbitrary figure. It falls out of the mathematics of 4 dimensions. A symmetric object with 2 indices in 4 dimensions has 10 independent components, and those 10 numbers, specified everywhere, tell you everything there is to know about the geometry. How far apart things are. How much time elapses along any path. What angles look like. How the curvature bends orbits, delays signals, stretches falling bodies. 10 numbers per point, and there is nothing else to say about the shape of reality. This object is called the metric, and general relativity is a set of equations for it. In 1976, Stephen Hawking, Anthony King, and Patrick McCarthy published a paper in the Journal of Mathematical Physics, proposing a way of building the topology of curved spacetime out of its causal structure. The result buried in it is the one that matters here. If you have 2 spacetimes, and there exists a mapping between them that preserves the causal order, which events precede which, and nothing else, then those 2 spacetimes are related by a smooth conformal transformation. The following year, in 1977, David Malamud sharpened the result in the same journal, showing that you need even less information than that. Knowing merely the class of continuous time-like curves, the possible histories of ordinary objects that can move, is enough to fix the topology of spacetime, and with it, the conformal structure. It is worth pausing on how ordinary Malamud's ingredient is. A continuous time-like curve is nothing more exotic than the history of a thing that can move, a spacecraft, a dust grain, a person walking to the kitchen. His result says that the set of possible histories of ordinary objects is enough to reconstruct the structure of the universe those objects move through. You do not need the geometry to get the histories, you can go the other way. None of this was a side interest for Hawking. He and George Ellis had spent the preceding decade rebuilding general relativity on global, causal foundations, and their 1973 book on the large-scale structure of spacetime is essentially a textbook of causal reasoning, large stretches of which never mention a coordinate system at all. So what does conformal mean, and how much of the 10 does it get you? It gets you 9. The causal structure, that bare ledger of yeses and nos, determines 9 of the 10 numbers at every point in the universe. Every fact about shape, every angle. Which directions are time-like and which are space-like. The full pattern of curvature. Where the horizons are, where the singularities are, how the light cones tip and lean around a rotating mass. 9 out of 10. The 10th is the overall scale at each point, and the reason it escapes is easy to see once it is pointed out. Take the metric at some point, and multiply the whole thing by a positive number. Every distance and every duration in that neighborhood changes together, in the same proportion. But the light cones do not move at all, because the cone is defined by the ratio of space to time, and multiplying both by the same factor leaves the ratio untouched. The ledger is unchanged. Not one yes becomes a no. Angles survive, sizes do not. The shape of everything, and the size of nothing. And there is a clean physical statement of what the missing number is. It is a volume element, how much space-time volume each region contains. Give me the causal order, and give me the volumes, and the metric is uniquely determined. There is no third ingredient. There is nothing else to know about the geometry of the universe. This is why physicists draw the diagrams they draw. When a relativist wants to show you the whole structure of a black hole, or of an infinite expanding universe, they draw a small diagram on a page with light rays running at 45 degrees, and they will happily squash an infinite space-time into a finite triangle to do it. Those pictures work because throwing away the scale throws away nothing causally relevant. You can still read off what can reach what, whether a singularity is in your future or off to the side, whether a horizon exists, whether a region can ever be seen. The distances are gone, deliberately, and none of the physics that matters goes with them. Light itself, incidentally, cannot tell the difference. Massless particles travel on paths that depend only on the conformal structure. Light does not know how big the universe is. It only knows its shape. There is a piece of history that makes this concrete, and it happens to be the most expensive mistake Einstein ever made. Between 1913 and late 1915, Einstein talked himself out of general relativity. Working with Marcel Grossmann on a draft version of the theory, he constructed an argument he called the hole argument. Take a region of spacetime with no matter in it, a hole. If your field equations are generally covariant, meaning they hold in any coordinate system, then you can smoothly shuffle the points around inside that hole and produce a second solution, different looking, equally valid, identical everywhere outside. Specify the entire universe outside the hole, and the theory still cannot tell you what the field is at a particular point inside it. To Einstein, this looked like a total collapse of determinism, and he drew the conclusion that generally covariant field equations were impossible. He then spent roughly 2 years building a weaker theory around that conclusion, a theory which, among other problems, gave the wrong answer for the orbit of Mercury, a discrepancy he knew about and lived with. In November of 1915, he abandoned the objection and wrote down the equations that carry his name. The resolution is the reason we are talking about it. The two solutions inside the hole are not two physical situations. They are one physical situation described twice, because the points of spacetime have no identity apart from the fields defined on them. There is no such thing as the point where the field would have been, independent of the field. Shuffling the points is the same operation as moving the entire universe 10 meters to the left. Einstein reproduced Leibniz's mistake 200 years later in his own equations, with his own hands, and had to accept Leibniz's answer before he could write down the theory. Modern relativists state the moral without much ceremony. Space-time points are not entities that carry identity. Only relations are physical. Let us stop and stack all of this up, because we are halfway through and the ground has been moving. We started with a bucket and a philosopher's question about moving the universe 10 meters. Newton said, space is a container. Leibniz said, space is a set of relations. The argument ran for 2 centuries with no way to settle it. Then relativity arrived and removed the universal present, leaving the interval, and the interval sorts every pair of events in the universe into 3 classes according to whether influence between them is possible. That sorting is the light cone, and the cone turned out to be a statement about causation, not about light. Rob showed you could rebuild flat spacetime geometry from the ordering alone. Zeeman showed the symmetries of relativity are exactly the transformations that preserve that ordering. And then Hawking, King, McCarthy, and Malamud showed that in curved spacetime, in the real universe, with gravity, the causal order determines 9 of the 10 numbers that describe the shape of reality, which leaves 1 number outstanding. 1 number per point, the size of things, missing from an otherwise complete account of the universe. You would expect that gap to be a problem. In 1987, 4 physicists proposed that it is the opposite, that the missing number is the single biggest clue we have about what space-time is actually made of, and that supplying it requires the universe to be, at the smallest scale, not smooth at all. Part 8. Order plus number. If causality gives you 9/10 of geometry, and the missing tenth is a volume, then there is an obvious thing to try. Build a theory out of exactly those 2 ingredients, and nothing else. That is what Luca Bombelli, Juhan Lee, David Meyer, and Raphael Sorkin proposed in Physical Review Letters in 1987, in a paper called Space-Time as a Causal Set. It is one of the shortest and most severe proposals in modern physics, and Sorkin's summary of the entire program is 4 words long. Order plus number equals geometry. Here is the whole framework. The fundamental thing is not a smooth manifold, not a field, not a string, not a wave function. It is a set of discrete elements, call them events or atoms of space-time, with a single relation defined on them, precedes. And that relation has to obey 3 conditions. First, it is transitive. If A precedes B and B precedes C, then A precedes C. This is just the statement that influence chains together. Second, it is acyclic. Nothing precedes itself. There are no loops, no journeys that come back to their own beginning. Causation goes one way. Third, and this is where the theory does something the others do not, it is locally finite. Between any 2 elements, there are only finitely many other elements. Not an infinite dense crowd, a countable, finite number. That third condition is the whole trick, and it is doing the job that no continuum theory can do. Think about why the continuum needed a volume element bolted on in the first place. In a smooth space-time, any region, however small, contains infinitely many points. You cannot measure a region by counting what is in it, because the answer is always the same: infinity. So volume has to be supplied separately, as an extra structure, on top of the causal order. In a causal set, the answer is different. Ask how big a region is, and you count the elements in it. The number is the volume. The missing tenth of the metric is not an extra ingredient that has to be imported from somewhere. It is what discreteness hands you automatically. Causality gives you the shape. Counting gives you the size. Nothing else is needed, and nothing else is permitted. The natural scale for the counting is the Planck scale. A Planck length is about 1.6 times 10 to the minus 35 meters. A Planck time is about 5.4 times 10 to the minus 44 seconds. Multiply the cube of one by the other, and you get a 4-dimensional volume of space-time so small that the numbers stop meaning anything. It is to a proton roughly as a proton is to the solar system, and then some. At 1 element per Planck 4 volume, the entire history of the observable universe, everything, everywhere, from the beginning to now, is a set of something like 10 to the power of 240 elements, a 1 with 240 zeros after it. That is the number of atoms of history in the world we can see. Now, how does a structure like that relate to the smooth space-time we actually experience? Through a procedure called sprinkling, and the details of it produce one of the most peculiar requirements in physics. You take a region of ordinary smooth space-time. You scatter points into it at random, genuinely at random, by a process where the expected number of points in any region is proportional to its volume, with no coordination between them at all. You then let each pair of scattered points inherit the causal relation they had in the smooth space-time, and throw the smooth space-time away. What remains is a causal set, and if the density is high enough, it contains essentially all the information the original space-time had. The obvious question is why on earth it has to be random. A neat grid would be so much easier to work with. The answer is a theorem, and it is beautiful. A regular lattice cannot be compatible with relativity. Lay out a grid of points, evenly spaced, at rest, with respect to some frame, and then boost it. Look at it from a frame moving at high speed relative to the first. The grid does not look the same. Distances along the direction of motion are contracted, so the spacing changes, and the lattice you get is a different lattice, which means the original grid secretly picked out a preferred frame, the one in which it looks regular. And relativity's entire content is that there is no preferred frame. A random sprinkling behaves completely differently. Because the points are scattered by a process with no correlations, boosting the whole arrangement produces something that is statistically identical, a different specific scatter, but drawn from exactly the same distribution, with no way to tell which frame it was generated in. Bombelli, Joe Henson, and Sorkin proved this formally in 2009, in a paper whose title states "The Moral Discreteness Without Symmetry Breaking." Sit with what that requires. If reality is granular at the smallest scale, the grains cannot be arranged in any orderly way. Not a lattice, not a crystal, not a honeycomb, not any structure with regular spacing, because every one of those would pick out a frame and violate the deepest symmetry we have ever tested. The fundamental structure of the world, if it is discrete, has to be irregular, scattered like static, random at the level where randomness is not a description of our ignorance but a requirement of consistency. And the room you are sitting in, which appears entirely seamless, the smooth air, the continuous surfaces, the unbroken space between your hand and the wall, would be the statistical appearance of something with no order to it whatsoever at the bottom. Smoothness as an average, in the same way that the grey of a printed photograph is an average of scattered black dots, and there is no grey anywhere in the picture. The program has a claim to fame, and it is not a retrodiction. It is a prediction that arrived before the observation. In the same period, Sorkin ran the following argument. If space-time volume is a count of discrete elements, then the count has to fluctuate. Counting processes always do. Scatter a random number of things, and the number wobbles by roughly the square root of itself. Now, in general relativity, there is a quantity that is conjugate to space-time volume, the cosmological constant, the energy of empty space. If the volume fluctuates, then the constant does too, and it cannot sit at exactly 0. It should have a residual value of order 1 over the square root of the number of elements. Run that arithmetic for our universe, and you get something around 10 to the minus 120 in natural units, small, not 0, and roughly the size of the mysterious energy that was discovered in 1998 to be accelerating the expansion of the universe, the observation that won the Nobel Prize in 2011, and that nobody has satisfactorily explained since. The prediction preceded the observation by about a decade, and it was made for structural reasons, not by fitting anything to data. There are honest caveats. The argument gives an order of magnitude rather than a precise value, and getting a full working dynamics out of it remains open. But if it is right, the reason the universe is being pulled apart is that the universe cannot count itself exactly. This is not a finished theory. It has serious open problems, the sharpest of which is a strange kind of non-locality. In a random sprinkling, an element's nearest neighbors in the relativistically correct sense are smeared all along its light cone, and there are enormous numbers of them, which makes ordinary local physics unexpectedly hard to recover. But it demonstrates the point that this whole video has been building toward. You can take a universe, delete space, delete time, keep only a list of what can influence what, add the ability to count, and get the world back. Which raises a question nobody was asking in 1987, because it had already been answered 20 years earlier by a man who worked out what a black hole is by thinking about nothing but causal relations, and who noticed the crucial idea while crossing a road. Part 9. The street crossing. In the early 1960s, most physicists did not believe in black holes. The mathematics permitted them. Carl Schwarzschild had found the relevant solution in 1916, within months of general relativity being published, and it contained a place where the equations broke down and the density went to infinity. But everyone knew how that solution had been obtained, by assuming perfect spherical symmetry, a perfectly round star, collapsing perfectly evenly, with every piece of matter falling exactly toward the center. Real stars are not like that. Real stars spin, they have lumps, they are turbulent, their magnetic fields are tangled, and their collapse is messy. The reasonable expectation was that in any realistic collapse, matter would miss the exact center, swirl past it, and bounce, producing something dense and violent, certainly, but not an actual infinity. The most influential version of this argument came from the Soviet physicists Yevgeny Lifshitz and Isaac Khalatnikov, who published an analysis in 1963 concluding that singularities were artifacts of unrealistic symmetry and would not occur in nature. Roger Penrose thought the whole question could be settled without solving the equations of stellar collapse at all, without knowing anything about the star's composition, its rotation, its magnetic field, or its shape. He thought it could be settled by reasoning about causal structure. In the autumn of 1964, Penrose was walking through London with a visiting colleague, the physicist Ivor Robinson. They had been talking without pause for some time. Robinson was an engaging talker, and the conversation had been going on all the way down the street. They reach a side road. The traffic is coming. The conversation stops, mid-thought, because crossing a road in London requires attention. They step off the curb, cross, step up on the other side. Robinson resumes talking, and the conversation closes over the gap, without either man noticing there was one. Some time later that day, after Robinson has gone, Penrose notices that he feels unaccountably good, not pleased about anything in particular, just a low, unfocused elation, of the kind that usually has a cause. He is a careful person, so he goes looking for it. He works backwards through the day, hour by hour, checking each thing that happened against the feeling, and finds nothing that fits, until he reaches the moment, in the middle of the afternoon, when the conversation stopped for a side street. And in that silence, in the 10 seconds of crossing a road, an idea had arrived, and the resumption of the conversation had buried it before it could be examined. He digs it back out. It is the notion of a trapped surface. Here is the idea he retrieved. Take any closed two-dimensional surface. Think of a sphere drawn around a collapsing star, and imagine a flash of light emitted from every point of it at once. Normally two things happen. The light emitted outward expands, so the outgoing wavefront covers a larger and larger area. The light emitted inward converges, and its area shrinks. Outward grows, inward shrinks. That is what surfaces do in ordinary space. A trapped surface is a surface where both of them shrink. The geometry is so strongly curved that even the light emitted directly outward, traveling outward at full speed, encloses a smaller area a moment later than it did when it left. Nothing about the shape of the surface matters. Nothing about symmetry, rotation, lumpiness, or composition matters. Once the cones have tipped that far, every future directed path, every path anything can take, leads inward. Penrose's paper appeared in Physical Review Letters in January of 1965. It runs to 3 pages. Using only causal and topological arguments, with no symmetry assumptions and no equations of stellar structure, it establishes that once a trapped surface forms, and given some reasonable conditions on energy and on the overall causal structure of spacetime, the spacetime must be geodesically incomplete. That phrase is the technical definition of a singularity, and it is worth stating precisely, because it is not what most people picture. It does not mean a point of infinite density sitting somewhere. It means that there exists a path through space-time, the history of some possible object, that simply ends. Follow it forward, and after a finite amount of elapsed time there is no more space-time to follow it into. A history stops, and physics has nothing to say about what happens next, because there is no next. Lifshitz and Kalatnikov, to their considerable credit, examined the argument and publicly accepted it, revising their position. That is an unusually clean way for a theoretical dispute to end. Hawking, then a graduate student, took the same machinery within a year and ran it backwards in time, applying it to the universe as a whole rather than to a collapsing star. The joint Hawking-Penrose theorem of 1970 extended it further. Penrose received the Nobel Prize in 2020, more than half a century later, for the discovery that black hole formation is a robust prediction of general relativity. The thing to notice is what the proof used. Not a single equation about the star, only the structure of what can influence what. And the definition of a black hole that came out of this work is stranger than the one in the popular picture. The event horizon is not a surface made of anything. It is not a place where the equations do something special. It is defined like this. It is the boundary of the region from which no future directed path ever reaches infinity. That definition refers to the entire future of the universe. It is not local, and it cannot be made local, which means there is no measurement you can perform at the horizon that tells you that you are there. Imagine falling toward M87, the supermassive black hole at the center of a galaxy 55 million light-years away, imaged by a network of radio telescopes in April of 2019. It is about 6.5 billion times the mass of the Sun, and its horizon has a radius of roughly 120 astronomical units, larger than the orbit of Pluto around the Sun. You are falling. Nothing is happening. There is no membrane, no shimmer, no boundary of any kind. Your instruments show nothing unusual, because there is nothing unusual to show. The curvature at the horizon of an object this large is gentler than the tidal stress you experience standing on the Earth. You feel no jolt, no pressure, no transition. You would cross the most consequential boundary in the universe and have no way whatsoever to know that you had. The only method of detecting it is to try to leave and discover that every direction you can steer toward, including the one you came from, now leads deeper in. Two more strange properties follow from defining a boundary by its future. The first is that tidal forces at the horizon get gentler as the black hole gets bigger, falling off with the square of the mass. For a black hole of a few solar masses, you would be pulled apart long before arriving. For M87, you would cross without sensation. The larger and more consequential the object, the less it announces itself. The second is stranger still. Because the horizon is defined by what will never escape, its position depends on what happens afterwards. Drop a load of matter into a black hole tomorrow, and the horizon as it existed today was already, in retrospect, slightly larger than it appeared. The boundary has, in a real technical sense, already accounted for its own future. It is not that information travels backwards. It is that the horizon was never a local object in the first place. It is a fact about the whole causal structure, read off after the fact. The most famous edge in the universe is not made of anything, cannot be detected by anyone crossing it, and its location depends on things that have not happened yet. That is what it looks like when a boundary is made purely of causal relations. Which raises the question that has been waiting since we started. If the causal structure is the fundamental thing, and it is a fixed pattern of relations laid out across the whole of history, then in what sense does anything happen at all? Part 10. The block and the letter. If the causal order is what is fundamental, then the natural picture that follows is a static one. The reasoning is short. If every event has its place in a fixed pattern of relations, this one before that one, this one unreachable from that one, then the pattern is the reality. And a pattern does not happen. It simply is, laid out complete, all of it at once, with no part of it more real or more present than any other. The whole history of the universe, from whatever counts as its beginning to whatever counts as its end, as a single four-dimensional structure, every moment of your life sitting at its own coordinates, permanently. This is the block universe, and it is not a fringe position. It is what a great many working physicists believe, and the argument for it comes straight out of relativity. Here is the argument. Relativity says there is no universal present, no privileged slicing of the universe into everything happening now. Different observers slice it differently, and none of them is correct. So consider some event that you would call future, and that another observer, moving relative to you, would call present. If we agree that whatever is present is real, then that event is real for them. And reality is not the sort of thing that can be true for one person and false for another standing next to them. So it must be real for you too, even though it is in your future. Wim Reetdijk in 1966 and Hilary Putnam in 1967 turned that into an explicit argument that relativity entails the reality of all times, past, present, and future alike, all equally existing, with now being nothing more than a label attached to whatever slice you happen to occupy. Penrose gave the argument a form you can picture, and it involves two people on a pavement. Two pedestrians pass each other on a street, walking in opposite directions at ordinary walking speed. Nothing exotic, no spaceships. Because they are in relative motion, their planes of simultaneity, their definitions of everything happening now across the universe, are tilted with respect to each other by a fantastically small angle. But an angle, extended far enough, becomes a large separation. Extend those two planes of simultaneity out to the Andromeda Galaxy, 2.5 million light-years away, and the tiny tilt has spread into a difference of a day or more. One pedestrian's now includes an event on Andromeda that the other pedestrian's now places firmly in the future. If there were a fleet on Andromeda deciding whether to launch, one of them would say, the decision has been made and the launch is underway. The other would say, the decision has not yet been taken and could still go either way. They are standing next to each other. They pass close enough to bump shoulders. Neither of them is wrong, and there is no third observer with the correct answer, because there is no correct answer to have. Now, that scenario does not prove anything by itself, and honest accounts should say so. No signal is passing, no one is learning anything about Andromeda, and the disagreement is about a labeling of distant events rather than about anything either pedestrian can act on. But the pressure it puts on the idea of a universal, objective present is real, and it has never gone away. The best-known statement of the block view is not in a paper, it is in a letter. In March of 1955, Einstein learned that Michele Besso had died. Besso had been his closest friend since their student days in Zurich, the man he thanked in the 1905 relativity paper, the one person he discussed the hardest problems with for 50 years. Einstein wrote to Besso's family, and in that letter, he wrote the sentence that gets quoted more than almost anything else he said. For those of us who believe in physics, he wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. He was 76. He died a month later. Hermann Weyl had said the same thing more coldly a few years earlier. The objective world simply is, it does not happen. Only to the gaze of consciousness, crawling upward along the world line of a body, does a section of that world come to life as a fleeting image in space, which continuously changes in time. Take the block picture seriously for a moment, because it is worth feeling rather than only understanding. If it is right, then nothing is ever lost. Every moment you have lived is still there, at its own coordinates, exactly as real as this one. The people you have lost are still located in the structure of reality, not in the past, in the sense of gone, but at particular positions, in a fixed four-dimensional pattern, doing what they were doing, permanently. And you cannot reach any of it, for exactly the same reason you cannot reach a space-like separated event. Not because it does not exist, because no path leads there. Nothing about your world line can be steered toward those coordinates. The block universe is not a consolation. It is a very precise description of loss. Everything preserved, nothing accessible. Now, several honest qualifications, because this is a place where physics gets oversold badly. The block universe is a picture, not a theorem. Relativity proves that there is no universal present. It does not prove that the future exists in the same way the past does. Those are different claims, and getting from the first to the second requires philosophical premises that not everyone accepts. There are alternatives that take relativity entirely seriously. The growing block holds that the past and present exist, while the future does not, with reality accumulating as events come into being, which keeps a genuine becoming while giving up the idea that the leading edge is a single global surface. Presentism, the view that only the present moment exists, is much harder to reconcile with relativity, since it needs a preferred slicing that the theory gives no way to identify. It is also worth saying clearly what the block picture does not settle, since the internet is confident about this, and should not be. It does not disprove free will. The relationship between determinism and human agency is a question that predates physics by well over 2,000 years, and nothing in a four-dimensional geometry resolves it in either direction. Anyone telling you that relativity has closed that question is reporting their own philosophical preference and attaching a physicist's name to it. And there is one awkward observational fact that relationalists like to point at. Our universe does hand us a distinguished frame in practice, the one in which the microwave background left over from the early universe looks the same in every direction. We are moving relative to it at about 370 kilometers per second, and that motion shows up as a lopsidedness in the microwave sky that has been measured with great precision. This is not a structural feature of space-time. It is a contingent fact about how matter happens to be distributed, but it does mean that in the actual universe, unlike in an idealized one, there is a slicing that is more natural than the others. Einstein's own position was less settled than the Besso letter suggests. The philosopher Rudolf Carnap recorded a conversation in which Einstein said that the experience of the now worried him seriously, that it means something essential for human beings, something fundamentally different from the past and the future, but that this important difference does not and cannot occur within physics. Carnap's account has him concluding that this was a matter of painful but unavoidable resignation. And there was one person who took the block picture, agreed with it entirely, and then used it as a weapon. He gave his argument to Einstein as a birthday present. Part 11. The Birthday Present. Kurt Gödel and Albert Einstein walked home together nearly every day. They were both at the Institute for Advanced Study in Princeton, and by the 1940s they had become close in a way that surprised the people around them, since neither was easy company. Einstein is supposed to have remarked in his last years that his own work no longer meant much to him, and that he came to the Institute mainly for the privilege of walking home with Gödel. Gödel was the greatest logician since Aristotle. He had proved, in 1931, that any formal system rich enough to describe arithmetic contains true statements it cannot prove, a result that closed off a program that mathematicians had spent decades building. He was also increasingly fragile, deeply solitary, and possessed of an unusual habit. When he became interested in a subject, he learned it completely and then found the thing in it that everyone else had missed. In the 1940s, At Princeton, he became interested in general relativity. For Einstein's 70th birthday, in March of 1949, Gödel gave him a solution to his own field equations. The solution describes a universe filled with uniform dust, rotating, not expanding, with a negative cosmological constant. It is a perfectly legitimate solution. The equations are satisfied exactly, the mathematics is unimpeachable, and it does not require anything physically absurd like negative mass. It is simply a universe that is allowed by the theory. Its feature is the rotation, and what the rotation does to the light cones. In Gödel's universe, the rotation tips the cones progressively as you move away from any given point. Near you, they stand upright in the usual way, and the future is straightforwardly ahead. Farther out, they lean. Farther still, they lean more. And beyond a certain distance, they have tipped so far that the direction we would call into the future has swung around to point back the way you came, in time as well as in space. The consequence is that you can leave an event, always traveling into your own local future, never doing anything strange, never exceeding the speed of light, never violating a single local law of physics, and come back to the event you started from. Not to the same place at a later time, to the same event, your own past, with you already there, about to leave. Through every single event in Gödel's universe, there is such a path. Not in exotic regions, everywhere. Gödel's point was not that time travel might be possible. He was not especially interested in travel. His point was philosophical, and he stated it in a companion essay published alongside the solution. In his universe, he argued, there is no objective lapse of time. There cannot be, because a lapse of time requires the universe to be sliceable into a sequence of moments, one after another, and in his cosmos, any attempted slicing eventually runs into its own past and closes into a loop. No consistent global ordering of moments exists. So in that universe, time does not pass, in any objective sense. And here is the move. If there are physically possible worlds in which time does not objectively pass, and if our world differs from those worlds only in the contingent details of how matter happens to be distributed, then the passage of time cannot be an essential feature of reality. It cannot be built into the structure of things. At most, it is a local accident, and more likely, it is something contributed by us. Gödel had taken relativity, the theory that made space-time a physical object, and used its own permissiveness to argue that the flow of time is not part of the world. Einstein's published response is worth reading for its discomfort. He acknowledged that the solutions were consistent, said they constituted an important contribution, and noted that they raised a question that had already disturbed him at the time general relativity was being written. Then he suggested, without much conviction, that such solutions might have to be excluded on physical grounds. They have not been excluded. Nothing in general relativity forbids paths that close on themselves. They appear in other solutions too, inside the ring singularity of a rotating black hole, around idealized infinite rotating cylinders, in the geometries associated with traversable wormholes. What rules them out, if anything does, is not the theory as written. It has to be added by hand, in the form of assumptions about what kinds of matter and what kinds of global structure are physically reasonable. The usual objection at this point is the one everybody reaches for. Surely a closed loop in time produces a contradiction, someone preventing their own departure, and surely contradictions rule the whole thing out. The standard reply in the literature is more subtle and more unsettling than that. It is called the self-consistency principle, and it says that only globally consistent histories are permitted in the first place. That if you travel around a loop, whatever you do on the far side is already part of the history that led you there. Nothing is changed, because there was never a version of events in which it was otherwise. The loop is not a paradox. It is a history that happens to be shaped like a circle, and the traveler's freedom to act is constrained by the requirement that the circle close. Whether that is a resolution or an evasion depends on how much you dislike the answer. The closed curves inside a rotating black hole are worth a sentence, since they are the most concrete case. The exact solution for a spinning black hole contains, deep inside, a region around the ring-shaped singularity where such loops exist. Almost certainly this region is not physically realized. A real collapse does not produce the idealized eternal geometry, and the inner structure is thought to be unstable. But the fact remains that the standard solution for the most common kind of black hole in the universe has a place in it where time closes on itself. Our universe is not Gödel's, to be clear. It is expanding, which his is not, and the observational limits on any overall rotation of the cosmos are extremely tight, far tighter than his solution would require. Actually traversing one of his loops would demand sustained speeds above roughly 70% of light, and a journey of order 100 billion light-years, which is a way of saying that the curves exist in the geometry and are hopeless in practice. But the principle stands, and it is uncomfortable. The most thoroughly confirmed theory of space and time we have does not, by itself, guarantee that causes precede their effects. That guarantee, the acyclic condition, the thing that the causal set program has to assume as an axiom, the thing this entire video has been treating as bedrock, is not delivered by general relativity, it is hoped for. In 1992, Hawking proposed a way to plug the gap. He called it the chronology protection conjecture, the idea that whenever a region of spacetime is about to develop closed time-like curves, quantum effects will intervene and prevent it, the vacuum energy of quantum fields diverging as the loop tries to close, destroying the geometry before the loop can form. The evidence for it is suggestive rather than conclusive, and a full proof would require a working theory of quantum gravity, which is exactly the thing nobody has. Hawking ended the paper with a line that has outlived the argument. The conjecture, he wrote, makes the universe safe for historians. It remains a conjecture, and the theory that would settle it, the one that would combine quantum mechanics with the geometry of spacetime, turns out to have a much more immediate problem with time than closed loops. When physicists finally wrote down the quantum equation for the universe, the equation had no time in it at all. Part 12. The equation with no time in it. Quantum mechanics and general relativity disagree about time in a way that is easy to state and has resisted 60 years of effort to fix. In quantum mechanics as ordinarily written, time is an external parameter. The Schrödinger equation tells you how a quantum state changes with respect to a t that sits outside the system being described, ticking along regardless of what the system does. Time is not an observable. There is no operator for it. It is a dial on the outside of the box, turned by nobody, and everything the theory says is phrased as a change with respect to that dial. In general relativity, there is no such dial. Time is part of the geometry, and the geometry is dynamical. It bends, it stretches, it responds to matter, and there is no external clock because the clocks are inside. Ask what time it is in general relativity, and the theory's honest answer is time along which path. Now try to write a quantum theory of the geometry itself. You need a wave function, not for a particle in space, but for space, for the geometry of the universe. And you need an equation telling you how it evolves. But evolves with respect to what? There is nothing outside the universe for it to evolve with respect to. John Wheeler and Bryce DeWitt tackled this directly. The story physicists tell is that the crucial conversation happened in 1965 in an airport in North Carolina, where the two men had arranged to meet during a layover and spent the time working through the problem. DeWitt's paper appeared in 1967. The equation they arrived at says that the Hamiltonian operator, applied to the wave function of the universe, gives 0. If you have met the Schrödinger equation, you will recognize what is missing. There is no time derivative, nothing on the right-hand side describing change. The equation is a constraint, not an evolution law. Applied to the universe as a whole, it describes a state that does not change, because there is nothing for it to change with respect to. The most direct attempt anyone has made to write down the quantum state of everything produced an equation in which nothing happens. This is called the problem of time, and it is not a technicality that is going to be cleaned up in a footnote. It has been sitting at the center of quantum gravity since 1967. The equation is not even well defined mathematically in the general case, which is one reason entire research programs have been built on reformulating the whole problem in different variables. But the structural point survives every reformulation. When you quantize a theory in which time is part of the dynamics rather than a background, the time disappears from the resulting equation. There are 3 serious responses, and all 3 are live. The first says that time is emergent, and that the appearance of change is internal to the universe rather than a property of it as a whole. In 1983, Don Page and William Wouters published a proposal along these lines. Take the universe to be in a single static quantum state. Now divide it into 2 parts, a small subsystem you will call the clock, and everything else. The static global state is not a product of the two. It is entangled, correlated, such that particular clock states are associated with particular states of everything else. Now ask not what is the state of the universe, but what is the state of the rest, given that the clock reads 3, and then given that it reads 4 and 5. You get evolution. You get a sequence of states of the rest of the universe, correlated with the clock readings, changing exactly as an ordinary Schrödinger evolution would have them change. But the global state has not moved at all. In 2013, Ekaterina Moreva and her collaborators in Turin built a toy version of this in the laboratory, using 2 photons. One photon plays the role of the clock. Its polarization rotates as it passes through a piece of quartz, acting as a hand on a dial. The other photon plays the role of the rest of the universe. The 2 are entangled, and the pair is prepared in a state that, taken as a whole, does not change. Now picture the experiment from the 2 available points of view. You are inside. You have access to the clock, and you can ask what the rest of the universe is doing when the clock reads a particular value. You look, and you find a world in motion. The second photon's polarization is in one state early, another state later, moving smoothly through a sequence, exactly as a physical system evolving in time would move. You would swear that things are happening. You would build a physics on it, and the physics would work. You are outside. You have no access to the clock as a clock. You can only measure global properties of the joint state, taking the whole toy universe as your object. You measure again. Nothing changes, not slowly, not subtly. The state is exactly what it was, and it will be exactly the same at every measurement you ever perform, because it does not evolve. There is no motion in it anywhere. Both descriptions are correct. They are descriptions of the same 2 photons on the same optical bench. Time exists for observers who are part of the system and correlated with a clock inside it, and does not exist for anyone able to view the whole thing from outside. And for the actual universe, there is no outside, so the only available viewpoint is the one that sees things happen. There is a variation on this response worth knowing about, because it makes time a consequence of ignorance rather than of correlation. Carlo Rovelli, working with the mathematician Alain Connes in 1994, proposed what they called the thermal time hypothesis. The idea is that a system described statistically, coarsely, in terms of averages, because nobody has access to every microscopic detail, automatically acquires a preferred notion of flow, generated by the statistical state itself. On this view, time is not fundamental and not merely relational, it is thermodynamic. The flow we experience would be a consequence of the particular blurred, macroscopic description we are stuck with, and a differently blurred description would generate a different time. The same research program has produced a picture in which space, too, is a network of relations, with areas and volumes taking discrete values, the smallest possible non-zero area being of order 10 to the minus 70 square meters. The second response goes further and says that time is an illusion at every level. Julian Barber has argued this for decades, most fully in a book published in 1999. On his account, there is no such thing as duration, no flow, no passage. There is only an enormous collection of possible configurations, complete, instantaneous arrangements of everything in the universe, each one a static snapshot he calls a now. They are not laid out in a sequence. There is no sequence. There is just the collection. Then why does anything seem to happen? Because certain nows contain structures that look like records, a photograph, a fossil, a memory, a page of notes, a particular arrangement of neurons that feels like remembering. Barbour calls these time capsules. A now containing coherent records of other nows will feel, from the inside, like a moment in a history, and the sense that you have come from somewhere and are going somewhere is generated entirely by the contents of the single configuration you are in. Not one thing moves. The impression of movement is a feature of the snapshot. That is a picture with a genuine claim on our attention, and it should be uncomfortable rather than charming. But the whole edifice, Page and Wouters, Barber, the entire project of getting time to emerge from something timeless, rests on a bet. The bet is that the problem of time is a technical obstacle, that the mathematics is hard, that the right variables have not been found, that with enough work, the world we experience will be recovered from a timeless foundation. And there is a serious minority who look at 60 years of partial success and stalled progress and ask a different question. Not how do we solve this, but is this a technical problem or are we conceiving of it the wrong way? Part 13. The Conservative Radical. Almost everything we have looked at tonight points one way. Causality is the deep structure. Geometry is derived from it. Space is a summary of relations. And time, being the ordering itself, looks like the most derived thing of all. A label on a fixed pattern. A feature of the perspective from inside. There is a minority position that accepts every step of that argument except the last one, and reverses it. Its most persistent advocate is the theoretical physicist Lee Smolin, who has spent much of his career working on quantum gravity and who has argued, in a series of books and papers over the past 15 years, that time is the one thing in physics that does not emerge. The argument does not begin with a metaphysical preference. It begins with a pattern of failure. Every serious attempt to eliminate time works partially. The formalisms are built, the mathematics is genuine, real results come out. And then, reliably, in every one of them, progress stops at the same place, the point where you have to recover the world we actually live in. How do you extract observable quantities from a frozen state, when every observable quantity we know how to define is defined at a time? How do you get ordinary dynamics back out? How do you recover a classical world with events happening in it from a structure with no happening in it? Decades of work by very capable people have produced technical advances everywhere else and almost nothing there. At that point, Smolin argues, a judgment has to be made, and it cannot be made by calculation. When a research program makes steady technical progress on some questions, and none whatsoever on others, for 50 years, you have to ask which kind of obstacle you are looking at. Is this a technical problem, hard mathematics, waiting for a better method, or is it a sign that the question is being conceived the wrong way, and that no amount of technique will help because the framing is wrong? The history of physics contains both kinds. The three-body problem was technical. It took better mathematics and eventually computers, and the physics was fine all along. The ultraviolet catastrophe was conceptual. No improvement in classical technique was ever going to fix it, because the classical assumption itself was wrong, and the resolution required inventing quantum mechanics. Nobody knew in advance which was which. The people working on each problem had to make a judgment about what kind of trouble they were in. Smolin's judgment is that the persistent failure to recover time from timelessness is the second kind. That the reason time keeps refusing to emerge is that it does not emerge. On that view, the picture flips. Causality is not a shadow cast by a pre-existing geometry laid out complete. It is the fundamental activity of the universe, the ongoing generation of new events from existing ones, event after event, and that generation is what time is. The block is not the reality. The block would be a description of a completed history, and there is no completed history, because the process is still running and always will be. And space, on this account, is what emerges. Take a sufficiently dense network of causal relations. View it coarsely, from a distance, at scales enormously larger than the relations themselves, and it will present itself as a smooth continuum with distances and directions in it, in the same way that a fabric presents itself as a surface when you stop looking at the threads. Space is the appearance a causal network takes on when there are enough relations to look at. That is a genuinely radical claim. It reverses the priority that this entire subject has assumed since Minkowski welded the two together. But notice something about it, because it is why Smolin describes it as, in a certain light, the conservative option. The alternative, the timeless one, asks you to accept that the single most immediate feature of your existence, the fact that things are happening, is an artifact of your position inside a structure where nothing happens. It asks you to treat the passage of the moment as a systematic error running through every experience any conscious thing has ever had. That is an enormous claim, and it is usually presented as the sober and scientific position rather than as the extraordinary one it is. The position that time is real asks you to accept a much smaller thing, that the world is, at bottom, roughly the way it appears in this one respect. Things happen. There is a next. The cost is that you have to explain why relativity forbids a universal now, and that is a real cost, and it has to be paid with actual mathematics. Some of that mathematics exists. There are reformulations of general relativity that trade away the relativity of simultaneity for a different symmetry, relativity of scale instead of relativity of time slicing, and reproduce the theory's predictions while keeping a preferred slicing. There are models in which the fundamental data are not positions in space, but energies and momenta attached to causal events, with spacetime emerging as a description of how those quantities get exchanged. None of these is a finished theory. They are demonstrations that the reversed picture can be built at all. The most striking consequence is that if time is fundamental and genuinely generative, then the laws themselves need not be eternal. A law is something that acts in time. If time is the fundamental process, laws can have a history. They can be shaped, selected, or evolved over cosmological ages, rather than sitting outside the universe as fixed and unexplained. Smolin has pursued this seriously, including through a proposal from the early 1990s, in which universes reproduce through black holes, with the constants of nature varying slightly at each birth and being selected across generations for values that produce more black holes. The suggestion that the laws might change is not new, and its earlier versions did not survive. Paul Dirac speculated in 1937 that the strength of gravity might be slowly decreasing over cosmic history, and that idea has been thoroughly killed. Laser ranging to reflectors left on the moon, together with the timing of binary pulsars, constrains any change in the gravitational constant to well under a 10 trillionth per year. What distinguishes the modern proposals is that they attach the evolution of laws to cosmological history and to the generation of events, rather than to a simple ticking dependence on time, precisely so that they do not collide with the measurements that finished Dirac's version. That idea is speculative, and its author says so. It is also, unusually for cosmological speculation, falsifiable in principle. It predicts that our universe's constants should sit at a local maximum for black hole production, so that any small change would reduce the count. That is a check somebody can run. Here is what I want you to take from this part, and it is not the theory. Two groups of highly competent physicists are looking at the same equations, the same experiments, and the same 60 years of failure, and coming to opposite conclusions about whether the passage of time is the most fundamental thing there is, or the most persistent illusion there is. They make the same predictions today. There is no experiment currently on anyone's bench that separates them. So the choice is being made on a judgment. Which set of unsolved problems smells like hard mathematics, and which set smells like a misunderstanding? That is what the frontier actually sounds like when you get close enough to hear it. Not certainty, and not confusion either. A considered guess about what kind of trouble you are in, made by people who have spent their working lives in it. And there is one more development, which arrived recently, and which does something neither side ask for. It takes the causal order, the structure this entire video has been building up as the bedrock underneath space, time, geometry, and everything else, and puts it into superposition. Part 14. The concept. There is one loose thread left, and it comes from putting two ordinary facts side by side. The first fact is that in general relativity, the causal structure is not fixed in advance. In special relativity, the light cones stand in neat rows like fence posts, the same everywhere, permanent furniture. In general relativity they tip. Put mass somewhere, and the cones in its neighborhood lean toward it. That is what gravity is. Not a force pulling on things, but the tilting of the structure that determines where things can go next. The causal order is not a rule the universe obeys. It is a field, with equations of motion, responding to what is in it. The second fact is that matter can be in quantum superposition. This is not controversial and not new. A single atom can be prepared in a superposition of two positions. The effect has been demonstrated with objects made of thousands of atoms. Now put them together. If matter determines the causal structure, and matter can be in a superposition of two configurations, then the causal structure it generates should be in a superposition too. The light cones would tip one way in one branch and another way in the other. And in that case, whether event A can influence event B would not merely be unknown, it would be indefinite. That was a theoretical worry for a long time. Then people worked out how to test a version of it. In 2012, Ognian Oreshkov, Fabio Costa, and Czaslaw Bruckner published a framework for describing quantum correlations without assuming any background causal order at all, asking what quantum theory permits if you refuse to assume in advance that operations happen in a sequence. They found that it permits processes with no definite ordering. The following year, Giulio Chiribella and colleagues described a concrete protocol called the quantum switch. You have two operations, A and B, and a control qubit. If the control is in one state, A happens before B. If it is in the other state, B happens before A. Ordinary so far. Now put the control qubit into a superposition of both states. The order of operations is now in a superposition of the two orders, not unknown to the experimenter, but genuinely, without a definite value, in the same way that a particle in a superposition of two paths does not have a path. The switch has been built. Photonic implementations in 2015 and 2017 measured what is called a causal witness, a quantity that cannot exceed a certain value if the operations happened in any definite order, including an order that was merely unknown. The bound was exceeded by more than a dozen standard deviations, and it is not only foundational, there are communication and computation tasks that can be completed with fewer operations when the order is indefinite than is possible with any definite ordering, which have also been demonstrated. The honest caveat matters, and I am not going to skip it. Those experiments sit on optical benches in ordinary flat spacetime, and there is a serious argument that what they realize is a controlled simulation of indefinite order rather than an indefiniteness of the causal structure of spacetime itself. Defenders reply that the operational structure is what physics is about, and that the same objection could be raised against any interference experiment. That argument is not settled, and anyone who tells you it is has picked a side. What is not in dispute is the mathematical fact: quantum theory permits causal order to be a variable rather than a backdrop. If space-time is quantum at bottom, then the ledger of yeses and nos, the thing that gives you 9/10 of the geometry of the universe, is itself something that can be superposed. So, let me tell you what the concept is. It is called causal structure. That is all it is. The bare pattern of which events can influence which. Not what caused what. That would require knowing the physics of every process. Just the raw skeleton of possibility. For every pair of events in the universe, one mark. Could the first have reached the second, or not? And the claim, which is not a philosophical position, but a theorem with a century of work behind it, is this: space and time are not the container that reality sits inside. They are what a network of causal relations looks like from within it. Robb showed in 1914 that you can rebuild the geometry of flat spacetime out of the single word after. Zeeman showed in 1964 that the entire symmetry group of relativity, every result about clocks and rulers the theory is famous for, is precisely the set of transformations that leave the causal order unchanged. Hawking, King and McCarthy in 1976, and Malamant in 1977, showed that in the real curved universe, with gravity in it, the causal order determines 9 of the 10 numbers needed to describe the shape of reality at every point. And the 10th is a volume, which is to say a count of how many events there are. The shape of everything and the size of nothing. Add the counting and you have the world back. That is the concept. And notice what has happened to the argument we started with. Leibniz asked what would change if you moved the entire universe 10 meters to the left, and Newton said it would be a different universe, and there was no way to settle it. 200 years later, Einstein constructed the same question in his own equations, decided it destroyed determinism, spent 2 years building the wrong theory because of it, and could only write general relativity after conceding that a location has no identity of its own. And the modern answer is more thorough than Leibniz could have hoped for. It is not merely that moving the universe 10 meters changes nothing. It is that where the universe is was never a description of anything, because place is not a thing that events sit in. Place is a summary of how events stand to one another in a structure of possible influence. You can see why so much of physics reads differently once you have this. A black hole's horizon stops being a surface and becomes what it actually is, the boundary of a region from which no future path escapes, undetectable locally, positioned partly by events that have not happened yet. A singularity stops being a place of infinite density and becomes a history that ends. The speed of light stops being a fact about light and becomes the slope of the cone, the conversion factor that decides which pairs of events can be connected at all. And the reason nobody can tell you what is happening right now on a planet in Andromeda is not that the news is slow. It is that the question refers to a relation that does not exist, which leaves the one thing tonight has not settled, and I do not want to pretend otherwise. Is the network finished, or is it still being written? If it is finished, laid out complete, every relation already in place, then the block picture is right. The passage of time is something contributed by observers embedded in the structure, and the most immediate fact of your existence is a feature of your point of view. If it is still being written, if the fundamental thing is the ongoing generation of one event from another, and space is the pattern that generation leaves behind, then time is the most real thing there is, and the completed block is a fiction we drew because we like finished pictures. Both positions are held by serious people. They make the same predictions today. The choice between them is currently being made on a judgment about which unsolved problems are technical and which are conceptual, and that judgment will look obvious to whoever comes after us, in the way that these things always do. So this is where I will leave you tonight. You have spent your whole life inside two things you never examined, and underneath both of them, there is a single structure, the pattern of what can reach what. Space is that pattern seen sideways. Time is that pattern followed along its length. The stage was never there. There were only ever events, and the relations between them, and the possibility of one thing affecting another. If you do not understand that concept, you do not understand reality. You only understand how to move around inside it. Which, most nights, is enough. But not tonight. Somewhere above you, right now, the light cones are leaning very slightly toward the mass of the earth, and every next thing that can happen to you is being decided by their tilt. Nothing is holding that structure up. Nothing needs to. It is not resting on anything. It is what everything else is resting on.